Good to go? All right, so hi everyone, thanks for coming. Welcome to our live wireless reverse engineering workshop. Glad you all could make it. Can I just have a quick show of hands? Was everybody who was at the talk yesterday? Is anybody not at the talk? Okay, no problem. Basically today we're going to be, or just to introduce ourselves real quick, my name is Matt Knight, this is Marc. We're both wireless security researchers. Today we're going to be running through an example of reverse engineering a wireless system live. And again, this is kind of just to emphasize our thesis from yesterday that you don't have to be a signal processing whiz or a math expert to be able to do impactful stuff in the wireless space. So we're going to start from zero and hopefully get somewhere with this pager system, and we'll all play along and have a good time as we go. So if we want, we can do a recap of some of the concepts from yesterday. Would that be helpful, or we can just jump right in? Maybe we'll run through it quickly if that's good with people. Yes. Sure. Great. So we'll just kind of recap the wireless basics. We're going to run through the workflow briefly, and then that's the process that we're going to be using to reverse engineer the system live as we go. Cool. So when we're talking about wireless systems, we're talking about the PHY layer. It's going to be the first. That's going to be the first step that we're going to try to crack, and then we're going to move up the stack and try to figure out the packet structure. So we're going to be characterizing exactly how the system uses the wireless medium to communicate. Just to introduce the system briefly, I'm sure you've seen things like this before. You go to a restaurant, and or at least we have these in America all over the place. You go to a restaurant, you put your name in, they give you one of these, and when your table's ready or your food's ready, this thing will buzz and tell you to come back up and collect it. Obviously, that's a wireless link that coordinates it. It's driven by this base station that has some numbers that you punch in and hit a button, and it'll page the corresponding pager. We bought this thing on Amazon. It was the cheapest one on Amazon Prime.
1 star.
one star rating. So we'll see how we do. But yeah, it's an example of a low complexity wireless system that should be a good target for today. So we're going to be looking at some pictures of spectrograms, just to recap what these look like. Most tools will visualize them with frequency on the x-axis and time on the y-axis. And it's just a way of visualizing kind of what's happening in the spectrum. And the way these pictures are actually put together is using a function called a fast Fourier transform, which essentially takes it takes your capture and basically splits it out into all of the frequencies that comprise it. So a basic kind of law or property of complex signals is that you can essentially model any discretely sampled signal as a summation of basically component frequencies. That's gets kind of mathy, but essentially what taking an FFT, the signal does is allows us to break it down into the corresponding parts, view it, basically view what's happening at different frequencies within the capture. So we'll be able to use this to visualize what our waveform looks like and be able to zero in on some of the key features here. So we're going to be using software-defined radio with this exercise. Once you've kind of characterized the waveform and know what modulation it uses, what frequency it uses, you would be able to take the insights that we'll glean from SDR and move to a hardware-defined radio. If you wanted to make it low cost or something that you could use lower power, for example, moving to a hardware-defined radio that supports the parameters that we identify with SDR will get you that. But software-defined radio is really awesome because it's flexible, and it's going to allow us to do a lot of that initial exploratory research to identify what's actually happening in the medium. So we walked through the methodology yesterday. These are all things that we're going to try to identify. The modulation is kind of a key question mark as to what's actually happening with this communication scheme. We're going to look at it and find out what it is and go from there. But essentially, the modulation is the function that maps our digital ones and zeros into the analog RF medium. It's kind of like the core element of these wireless PHYs. So that's going to be one of the first things that we're going to try to identify and characterize. And again, this is kind of the key concept from yesterday, this notion of what a symbol is. And a symbol simply refers to a discretely sampled state that represents some quantity of digital information. So when we build our receiver, we're ultimately going to be putting together a function or a series of functions that will extract the symbols from the waveform. So again, when we talk about symbol, the only thing or the concept to remember is that it's a discrete state that represents some amount of digital information. Is that good with everybody? If you have any questions or? Cool. And we'll be walking through this as we go. So just to recap kind of two common PHYs that we'll see. Really low complexity wireless systems are often built on FSK or some type of ASK. FSK is frequency shift keying, where the modulated parameter is the frequency. ASK, you're modulating the amplitude. It's the power of the signal on a single frequency. And PHYs can get more complicated. You can modulate multiple parameters in conjunction. You can do things like spread spectrum, where you use more bandwidth to make them more resilient. We have good confidence that the system we're going to be looking at is going to be pretty simple. So we shouldn't have to worry about any of these more complicated examples. I think we're going to have a nice low complexity thing to work through today. No new information there. Yeah, so again, kind of the core, our main objective today is to build a receiver to be able to extract information from this wireless communication system. If we get that fully characterized and there's time, we'll build a transmitter and try to set some of these things off too. So we'll start building a receiver because that's the hard part. And by doing that, we'll learn everything we need to know about the PHY, and then we can turn around and try to build a transmitter if there's time. So just to recap our methodology briefly, we essentially identified 6 steps that we can use to reverse engineer just about any low complexity wireless system. We're always going to start with open source intelligence research because that's going to make our lives quite a bit easier once we actually get into the weeds. But step 1 of kind of the applied bit is characterizing the channel. So there are going to be 2 elements that we're looking for here. The first is to identify the center frequency, and if there's a single channel, that'll just be one frequency. But if it's frequency hopping, there might be a couple different center frequencies that it will jump between. And the second element to identifying the channel is identifying how wide it is. So if we have an FSK or some sort of frequency modulated channel, we'll want to identify how much frequency that signal can traverse with that deviations. The second step is to identify the modulation, which again is the function that defines how our 1s and 0s get mapped into the analog medium. And we're going to try to rely on open source intelligence if it exists to do this. If not, we will look at the capture on the spectrum, and we'll try to share some insight as to how you can gain intuition for what a modulation is by looking at it. This part is kind of daunting at first. The intuition does come pretty quickly because a lot of the low complexity modulations that are used for systems like this are really just kind of variations on a few different algorithms. So we'll walk through kind of our process as we, in what's telling to us as we try to identify the modulation. Step 3 is to determine the symbol rate, which is how often that symbol state changes, and we'll use some popular tools to go through this and hopefully show some insight on how this part can be made easy. Step 4 is to synchronize, and again, this gets into some of the more coding-heavy parts of this, where you can actually start to write software rather than drive tools to implement this part. And this will be using things like the preamble and the start of frame delimiter to get our receiver to synchronize with the packet that's come in and figure out where to start sampling or where to start extracting the symbols from. And then step 5 is basically just to pull out the remaining symbols, decode them if they're encoded, and then figure out what's going on kind of at layer 2. So that's our methodology. We're going to be applying it live and kind of filling these different stages in as we go, and we get some insight about the PHY here. So with that, I think I'll hand it off to Marc, and Marc is going to begin by kind of leading us through some open source intelligence research. While he does that, I'm going to get to flashing these USBs. I'll come around and distribute them as they're ready.
Okay, so this device is a Q wireless calling system. Doesn't really have a brand name. Kind of a shitty device we just got on Amazon. Unfortunately, it doesn't have an FCC ID. It's not licensed apparently to operate in the U.S. We do have this user manual here, which has tells us here that it says working frequency 433.92 megahertz. So this gives us some insight about where the device is going to operate on the spectrum. Unfortunately, that's really all the data we have from the manual about how it operates from an RF standpoint. Apparently, it's a beautiful and fashionable designing. And the system greatly improved the work efficiency and avoid the client waiting in a long. So really high quality stuff we're working with here. So one thing we can do is start and just do some Googling around and see if there are any other devices that are perhaps other brands that have the same thing that might be FCC registered. Let me throw on a hotspot here. And so oftentimes you'll have multiple vendors selling devices from one OEM. Some vendors will register with FCC, some won't, and so it's certainly possible that there are other devices or other vendors with brands of this same thing here. So let's find out. Okay, there we go. So we're going to go to Google here. And so this is labeled the Q wireless calling system. So we'll just see what the internet has to say about this. Okay, here we go. We have the Amazon link here. So this is the product we bought. Unfortunately, it doesn't have any further information here, but we can see it's a very highly reviewed product. But it was the cheapest paging system we could get on Amazon with next day shipping. So if we, for example, put in, FCC ID, you can often find, mentions of FCC IDs for products elsewhere. There was this other brand, it looks like, that has the same product. Unfortunately, no FCC ID for this one either. So this is a case where we just have some, cheap Chinese product that really doesn't have any good documentation and no regulatory registration or certification. So that means that we're kind of stuck with this 433.92 megahertz figure from the user manual here, and we have to start looking at the spectrum to see what's actually going on. So I know Matt is still flashing some of these GNU Radio drives. Does anybody have GNU Radio installed on their laptop? Okay. So I think the next step we're going to go here is actually look on the spectrum in GNU Radio and start to see what the behavior is like. And before we do that, let's do one search. So there's this website called fccid.io. And this is essentially a mirror of the FCC equipment authorization database. And what's nice is they have all the documents in Google Docs, and so it's all indexed by Google. So we'll go site fccid.io, and we'll search for the Q wireless calling system. Okay. Yeah, unfortunately, with a lot of these type of devices that aren't registered, there's not a lot of information in some cases. And so, yeah, it looks like nothing comes up. That's a good match. So this is a case where our open source intelligence stops at the user manual. So I'm going to open up GNU Radio here, and we can start taking a look at what this actually looks like on the spectrum. So there's a tool called GNU Radio Companion, which is a flow graph creation tool with GNU Radio. And this allows you to kind of drag and drop these signal processing blocks and put together flow graphs for both looking at the spectrum and building transmitters and receivers without having to actually write any code or understand the math that's going on under the hood. So I'm going to start with a USRP source. This is just the source block for the software-defined radio that I'm using here. For the RTL SDR dongles, there's a source is the Osmo SDR source block, and this takes the data in from the software-defined radio, and then we can connect this to other blocks to do things such as visualize the spectrum. Yeah, let me put on a lower resolution here. Okay, there we go. Okay, so we have our source block. In this case, this is the UHD USRP source, but the Osmo SDR source is the one that works with these RTL SDR dongles. And the purpose of this is to just have, this connects to the SDR and sends this raw data into the computer. And so we know that we have a 433.92 megahertz center frequency, at least according to the user manual. So add a variable here that'll tell us our frequency. And with GNU Radio Companion, you have these blocks that are called variable, and this is just a Python variable. So when you run a GNU Radio Companion flow graph, it generates Python and executes that Python. So you can also do all this just writing the Python code. I prefer that way. Some people prefer GNU Radio Companion. It's just kind of personal preference. So we're going to name this frequency here and set it to 433.92 megahertz. And then we're going to set a sample rate. And so the sample rate is the number of samples per second that the software-defined radio sends to the computer. And so with the RTL SDR dongles, those cap out at around 2 megahertz. So we'll do the same here. So I'll set this to 2E6, so 2 megahertz. And then we'll set the gain on our radio here. I'll set that to, say, 20 decibels. And then in the properties for the blocks on the GNU Radio Companion flow graphs, you can fill in the values with the names of these variables, and it's just setting Python variables in these underlying objects. So we'll set our frequency to FREQ and set the gain to gain. In this case, I'm setting an antenna that's specific to the radio I'm using, so that won't apply with the RTL SDRs. And so now we have this block configured to take radio data in at 433.92 megahertz. And then I'm going to connect that to a baud line sync. So baud line is a spectrum visualization tool that we like to use. And this will allow us to just view a spectrogram of the data coming in from the radio. So what I will do here is run this, and we'll start to see some of this data. And then I'm going to start pressing buttons on this pager system and see what we happen to see. So plug this thing in. And so the general premise behind how this pager system works, you have 20 of these pagers. You can, take one, give it to a customer. You, I guess, hit the number and call, and then the thing vibrates to tell the person to come and get their food or what have you. And so what we're going to be trying to figure out is what the communication looks like going on between the space station and the pager. So there's one thing I forgot here with this baud line sync block. This has, it's kind of goofy, and there's this scale parameter which has to be set to 2 to the power of 15. So the way baud line takes data in, it expects fixed point 16-bit complex numbers, and we're starting with floating point numbers, and so we have to scale that up. Scale that to 2 to the power of 15, and we'll run this again. Then we should see some data here. Okay, so now we're looking at a spectrogram at 433.92 megahertz. And so if I take one of these pagers out and call it, we should see something happen on the screen here. Okay, and so in baudline, you can hit the space bar to pause the flow graph, pause the data going through, and then what we can do is zoom in here. I'm going to actually lower the gain on the radio. So what's happening now is that the gain is set pretty high, and so we're seeing what's called aliasing, where we see the same signal copied back and forth. So we should only see one clean signal in the middle there. So I'm going to go here and lower the gain on the radio. Lower this down to, say, 5.
Just to clarify what's happening there, the signal over the air is overloading the receiver, which is causing all those images to show up, the aliases. So if you see that sort of distortion, know that sometimes it's the front end, and you should try backing the gain off rather than trusting that that's what the signal actually looks like.
And it's common on, especially lower quality radios like these RTL SDRs. They just don't have very high quality radio component, and so you'll often see this aliasing where you have the same signal. You have one in the center and then multiple copies going out.
And one other note about baudline, it's a super powerful tool. It's really, really awesome for visualizing signals, but there are a lot of knobs to turn. So sometimes you have to get the configuration just right in order to get you sometimes will have to fiddle with the configuration to get the image that you're looking for to look just right.
And so one thing we can note here, it looks like the center frequency, so we set this, tuned the radio to 433.92 megahertz, but it's actually, if we see in the bottom right here, it's offset by 62.5 kilohertz. So the frequency that was specified in the manual is slightly off. So now we can go back in and actually update the radio so we're going to go in, going to offset this by 62.5 kilohertz. I'll run this again, and then we should see the signal at the center of baudline here. Okay. I offset that in the wrong direction, so let's go update this again. So we can go plus 62.5 kilohertz, and we'll run this again. Okay, so now we have a fairly clean looking signal that's in the center of our spectrum on baudline. And in baudline, what we can do is hit Alt and then the up arrow, and this will zoom in. And looks like I'll need to lower the gain a little bit more because it's hard to make out here, but we have a clear signal that's being transmitted in the middle of the spectrum here when I set up one of these pagers. Let me go in and lower the gain a little bit more. Just to 0. Okay. Zoom in. I'm going to actually have to move the radio a little bit away from this thing.
Crank up your scroll control as well. You right click on. Yeah. There's another thing about baudline. Where'd that go? Oh, never mind. The other way up. Disregard that.
Okay, and I'm going to move this. Okay. All right, let's try this again with the radio a little bit further away. That is an annoying sound. Okay. Okay. So what's happening is that this transmitter is pretty loud, and so it's making it difficult to make out the actual signal visually here. So I'm just moving a little bit further away. All right, I'll try this again. Okay.
Try just in the window too.
Yeah, yeah.
It's like that. This is work that Spectrum can.
Yeah. So with Baudline, there are, yeah, as Matt said, all kinds of knobs to turn to kind of change how the signal is visualized. And if we can't get a good, clean visualization in Baudline, there's a tool called in Spectrum we can use, which might provide a little better results.
Let's do the trick.
Yeah, looks like it.
Cool.
So after tweaking some of these color aperture parameters in Baudline, we can start to make out a little bit of what's happening. And so we can see it's still a pretty strong signal because we're so close, but we can see that the signal is going those three little short blips, then a long blip, then a short one. And then we have these two distinct things we see on there. And what's happening is that this is a type of modulation, or it appears to be, called pulse width modulation. And so this is a type of amplitude shift keying or amplitude modulation where the data is encoded in how long the transmitter is on. So in this case, we have what looks like a period of the transmitter being on for a short amount of time and then off, and then a different type of symbol which is on for a longer amount of time and then off. And so this is going to be likely either bits 1 or 0 there, and then the other bit 1 or 0 there. And so the pretty simple visual protocol to look at once we can kind of tweak the color settings here.
Yeah, but so real quick, the key insight that kind of tells us that is what? Anybody hazard a guess as to why we can think that this is ASK versus frequency shift keying or some other type of modulation? Yeah, exactly. So we can look at like the insight that we've gained from looking at the channel here, that we see a single center frequency and that there's no deviation. There's just a single frequency that the protocol occupies. So, if we saw the frequency jumping back and forth, that would indicate FSK since it's on a single channel, and instead it's the power that's being modulated, then it's something amplitude driven. So.
And these are pretty low-cost transmitters to implement because all you have to do is turn this transmitter off and on and off and on. You don't have to change anything about its other characteristics. And so it's common to see this type of on-off keying or pulse width modulation in these really low-cost devices. But so what we can do next is take a look at the same signal in Spectrum, and in Spectrum will allow us to determine what the symbol rate is. And again, the symbol rate is how often the symbol state changes. So it would be how many bits are transmitted in this case every second. So what I'm going to do is add a file sync to this flow graph, and the file sync is going to it's still going to send this data to Baudline, but it's also going to write that data to a file on disk, and then we can open that file on disk using this tool called in Spectrum and have another view at it. And so I'm going to run the flow graph again. I'm going to set off one of these pagers, except this time it's going to also write this data to a file on disk. So I'll take pager 17 here. Okay. Okay, so I will set this off, then stop the flow graph here. And so these pagers, I think, just continue to go off indefinitely until you put them back in the base, which is quite fun. Okay, so now we're going to have a file on disk with this data we just captured from setting off this pager. I'm going to open it in a tool called in Spectrum. And Inspectrum is just another tool, kind of like Baudline. It has some additional features. One big distinction is that with Baudline, you can pipe live radio IQ data into it. With Inspectrum, you're always going to be opening these files offline. So we just recorded this file, now we're going to open it in Baudline. This is this pager-17.iq, and this is a file we just recorded here at a 2 megahertz sample rate. And then, so Baudline scrolls vertically in time, and Spectrum scrolls horizontally in time. So I have this scroll bar at the bottom, and I'm just going to scroll over until I see some data here. Okay, so here we have some of these packets, and I'm going to zoom in here, and we can start to see the signal again. Okay. Let's see if we can tweak this to make it a little bit more clear here. Okay, I think what I might do is move this pager base station a little bit further away, because we're still having a difficult time making the signal out clearly because it's saturating the receiver here. So give me one moment. Matt, you want to set off the pager while I do another IQ capture?
Sure.
Okay, so we're going to do another capture here. This time, Matt's going to set off the pager over there, and I'm going to be doing the capture over here, and hopefully it'll have a little bit more distance so we can get a bit clearer of a signal.
Call button?
Yeah, so if you take out pager number 17, and then if you, I'll let you know when this is running here, so, and yeah, just give me one. Okay, then if you want to put it back in, take it out, and then page that again. Okay. Let's see how this looks. Okay. All right, so we're going to open this capture up in Inspectrum now and see if this looks any better. Okay, so I'll open up this pager17.iq file that we recorded again. And again, we're going to scroll horizontally in Inspectrum.
You might have to change your power settings.
Oh yeah, thank you. Okay, so here we have,
That's good.
yeah, so it's looking a little bit better. Okay, and so we have these red bars here, and this is similar to what we saw in Baudline, just in a horizontal view. And we have these 3 short bursts again at the beginning, and then a long burst and a short burst, and then 3 long bursts, then some more short bursts. And these are the actual bits that are modulated and sent over the air. And so with Inspectrum, it has this tool called cursors that allows us to measure the time that it takes for each of these actions to happen, and this allows us to figure out what our symbol rate is. So in this case, we're going to basically drag this on here. Then we can adjust this, and then as we line this up to the symbols we see visually, we're able to figure out what the symbol rate is here.
It might be helpful to drop a plot on there as well. So if you right-click there and you hit Add Derived Plot. So this is a really sweet feature that Inspectrum has. Basically, Inspectrum has some very basic demodulation functions built into it that you can actually use to help visualize the symbols even more accurately. So in this case, since we've determined that we're likely looking at on-off keying or an amplitude shift keying based modulation, we can add an amplitude-based plot, and then you can basically just drag this bar that it generates down on top of your waveform, and then adjust the gain settings by dragging the outer tabs in or out. and it will actually give you, at least in theory, will give you a better visualization into what's actually happening there. I can jump in here. So I'm eating my words now. This isn't coming out super cleanly, but sometimes this can be a very useful way for accelerating this process. So forget what I said. We'll use the frequency view.
So for a little better example, I have a cleaner IQ capture that I recorded this morning that I think will give us a better visual representation of this. So we have, this is a capture that I took earlier at a 10 megahertz sample rate. So we're going to load this up here. Okay. And so this is so a little bit cleaner capture here from earlier. So this allows us to more cleanly see what's happening there. So we have the clear distinction between the transmitter turning off, then on, then off, then on. So what we can do here is drop cursors on and simply line up these vertical lines with this cursors tool to the symbols here. And so we have these short symbols and these long symbols. And what it appears to be is that in each period, we have, for this bit, we have it's on for 1/3 of the period, then off for 2/3. And then for this other bit, so we'll call this 1 and call this 0. So for bit 0, we have it on for 2 each of these periods, and off for 1. So
and real quick, for anybody who was at the talk yesterday, does this look familiar to any of the examples that we saw? So this is a very similar modulation to the siren that we saw, where it was, again, using amplitude, and it was using a pulse width type encoding scheme, where if the pulse is high for basically 3 symbols and then low for 1, it would be a digital 1, and if it was high for 1 and then low for 3, it would be a 0. And we're cheating a little bit just because we've looked at other systems like this. And if you have an OOK-based modulation, it's pretty common to see a pulse width type encoding scheme placed on top. And this is the sort of thing that you'll just gain intuition for as you do more of these. So that caveat.
And we can see that these vertical lines don't perfectly line up with the edges of each symbol. This is because it's in these low-quality systems, the timing is never perfect, and so there's always going to be some kind of variation there. So what we can do is zoom out a little bit more until we can see the entire packet here, and then we can actually add these cursors for the full length of the packet, and then we can see what the symbol rate is, and also what the total number of bits in the packet is going to be. Okay, so we have the symbols drawn across one entire packet here, and we can see that it's 75 symbols, but that said, each symbol, each vertical line is representing 1/3 of a bit, because each bit is going to be either on or off for 2/3, and then either on or off for the other third. So we have 3 symbols as listed there per bit. So that says 75 symbols. That means we have 25 bits for each one of these packets. And down there at the bottom, it says the symbol rate is 2.7526 kilohertz. So this is a symbol rate. This is 3 times the symbol rate because we have 3 vertical lines per symbol. So this means we have about a 900 baud protocol, so around 900 bits per second. And I'm going to open up another IQ file here. This is from another capture, and what we can do, this is, so the first capture there was calling one pager. We're going to look at a capture calling another pager and just verify that the packets look roughly the same, that we have the same number of symbols here, and that about lines up. So it looks like when you call any pager, the packet length is going to be the same. We're going to have about the same number of bits there. So is everybody getting closer to set up with the RTL SDR on GNU Radio? I think it might be good once we have anybody who wants to get set up, we can start setting up this page a little bit more and make sure that you all can see this data on your laptops.
Yeah, so, once we get all the rest of these USBs flashed, we'll go back and we'll send some signals out. We'll help everybody get set up with a GRC file flow graph to capture the waveform, and then we'll help you visualize it and start reproducing this on your own system as well.
Are those additional tools you mentioned on this image?
In Spectrum and Baudline, you'll have to install yourself. Baudline, because it's a closed source, it's not permissively licensed, so we can't distribute it. And then Spectrum requires a DSP library that I believe is also restrictively licensed.
Yeah, so Baudline is available at baudline.com, a nice modern website.
Yeah, I recommend downloading Baudline just because it's a single binary, it's a one shot.
Yeah,
it's the most condensed tool.
Definitely a great tool. The big problem with Baudline is that it's closed source. It's the guy who writes it hand codes the assembly, so it's highly optimized, but unfortunately not as reconfigurable as not as flexible as some of the other tools. And the other tool is called Inspectrum. And I believe Inspectrum is available through apt if you're on a Debian machine. But it's also available on GitHub here. And again, Inspectrum is a tool we were just looking at that has the time scrolling horizontally. Baudline has the time scrolling vertically. And then there is one GNU Radio module that is necessary to wire up Baudline to GNU Radio if you want to view the data live with Baudline. That is gr -baz.
This isn't required though. You can always view captures offline.
Yeah.
Just if you want to do the streaming view as Marc has been showing, it's something that's required.
And then while you guys are pulling down Inspectrum and Baudline, I'm going to set up a flow graph to retransmit one of these captures that we took earlier so we can have a constant amount of data coming out for you guys to look at with these RTL SDRs. Okay, so this flow graph I'm creating right now, this is just going to be reading in one of these IQ files that I recorded earlier and then transmitting it out using this USRP software-defined radio. And that will give us a kind of constant repeating signal that's identical to what this pager system is transmitting. And this throttle block, if we read in from this file source and we don't have a throttle, it will run at the absolute maximum rate it can. Because we're going into a software-defined radio that has a fixed sample rate, we don't necessarily need this, but it's always good to have a throttle block after your file source. and I'm setting the frequency to the 433.92 megahertz that was specified in the manual, and then we're adding that 62.5 kilohertz offset that we observed.
And who had this one? SanDisk? What's that? I unfortunately couldn't get yours to flash.
Oh, no.
Yeah, I'm sorry.
All right.
Couldn't figure it out.
Yes, I'm running the
Cool.
Just repeating the one page right earlier.
Sounds good. So basically what Marc is doing right now is he's basically retransmitting that signal. So what I'm going to do now is I'm going to walk you through setting up a GRC flow graph to capture this waveform, and then we can start to analyze it and look at it offline. So anybody who has an environment set up, feel free to open up GRC and follow along, and definitely just like raise your hand or shout out if you have any questions. We do this. So first thing we're going to do is we're going to open a new pane. You can just Control N to do that, and then we're going to first drop in our driver. And if you're using an RTL-SDR, that's going to be the Osmocom driver, Osmocom source. And sync versus source. A sync is something that consumes samples. A source is something that produces samples. So since we're using our radio to receive samples from the environment, it's going to be producing samples that we're going to be consuming. So drop in our source block here. It's got a whole bunch of parameters, and I'll walk through setting them up. When you're defining parameters, I always recommend you do so in a variable so that these flow graphs will be easily extensible and reusable. And that makes it so that, if you're capturing a sample, if you're capturing a sample at one frequency and you want to go look at a waveform that lives somewhere else in the spectrum, all you have to do is just reconfigure the variables and you're good to go. So you can reuse a lot of your tools that way. So the sample rate, Marc, what were you capturing it before?
2 megahertz.
2 megahertz. We're going to capture at 1 megahertz just because the ceiling of the RTL-SDR is like 2.2 and change. So sometimes, especially if you're on a live USB, getting the maximum performance out of the RTL-SDR over USB can be sketchy. So we're going to capture at 1 megahertz, so 1 E6. And you don't have to be super precise about this. The key thing is that you want to make sure that you're sampling at a fast enough rate to give yourself enough margin with the data rate, with the signal that you're observing. And this kind of gets into some of the mathier bits here, but basically within communications theory, you have to be sampling at a certain margin above basically the symbol rate that you're observing. So with software-defined radio and modern tools, just set your sample rate high when you're getting started, and then you can always reduce it later. The only thing it's going to cost you is performance, basically. So we've got a block for our sample rate. The second thing we're going to do is we're going to create a block for our frequency. We'll just name this freak, F-R-E-Q. What was your center?
So 433.92 plus 62.5 kilohertz.
Plus 62.5?
Yeah.
Okay. So what we're doing here is we're plugging in the center frequency that we expect our signal to live at. So 433.92 plus 62.5 kilohertz. And E6 is for megahertz, E3 is for kilohertz. So we'll plug that in there. Then we can come down here to our driver and we can populate in these variables. Just double click on that to open it up. Sample rate is pre-populated. And then the frequency we can just replace with freq, F-R-E-Q, so variable name. I believe none of these gain values matter because I'm pretty sure the RTL-SDR is just a fixed gain. So you can just leave those as is. So there's our driver. And now the second thing we're going to do is we're going to create a file sync to push these samples into. So, by the way, to search for these modules, you can Control F, and that pops up that tab, and then you can just type in the name. Otherwise, you can navigate to them through these kind of interactive browsers here. So Control F, File, Sync, like so, and then you're going to grab just the conventional file sync under the File Operators tab, and then we can just find a location on the hard drive to put this. I think it's Scratch.
Yeah, Scratch 44con.
Scratch 44con pager.
Yeah.
Cool. We'll just call this testrx.iq. And then you can leave unbuffered and append to default. So one last note I'll mention about GRC is you may notice these colored blocks here. Those are basically ports into and out of these separate DSP functions. The color of the port refers to the data type that will be either produced or consumed by that block. So in this case, the blue port like this means that it's a complex data type, complex float specifically. Basically, it's like the closest it's essentially digitally sampled radio information, very raw, that we're going to be capturing a disk. And you can connect them just by clicking and dragging. And some of the other data types that GNU Radio can support, I mean, you can see them all here in they're labeled here nicely. Complex float is what we have currently, but it supports many other data types as well. One other nice feature of GNU Radio that we're not going to be talking about is it actually supports packetized data as well. So there's a really nice asynchronous API as well as this synchronous interface that we're going to be using today. These are all kind of more advanced features. We don't have to worry about it, but they're there if you want them. So with this set up, you should be able to save your flow graph and then click this play button here to execute it. And that will pull in some samples and just store them to disk. And when you run it like so, there won't be any visual feedback. You won't be able to see the spectrum. If you want to see what's going on, you can drop in an FFT as well, fast Fourier transform, and that'll give you a visual indicator to make sure that you're looking at the right part of the spectrum as you capture. So you can just control and click for FFT, and then you can grab an FFT from the instrumentation page. I'm going to grab the WX, which uses the WX graphics engine. And since I'm doing that, I'm just going to have to change the graphics module under the top block here to WX. It's Qt by default. So double click and change it to WX. Drop that in. Plug that in there. Should be good to go. And will I be able to capture this while
Sure, yeah.
while the USRP is running?
I assume the also block will auto-select the...
Yeah, I'm more wondering about two different schedulers. We'll give it a go. So we'll see if this will work because the USRP is running too. It doesn't look like it. So I'm going to turn off the USRP for a minute, and then we'll just do it with the... Is this running?
Yeah.
Okay. Cool. Okay, there we go. So Marc, do you mind triggering the...
Oh, actually, yeah, I didn't see it running on the user, so this wasn't putting up RTL. Yeah, let me hit major.
So here we can see that this FFT is showing us that we're looking in the right spot. Would you mind triggering it again? So we can see the spectrum responding accordingly. So once we have a capture, we can just stop recording and that'll stop writing to disk. Is everybody good up to this point? They have their flow graph up and running. Assuming you want to play along, you're able to capture. Sure. Which would you like me to expand? Oh, okay. So, yeah, so run through real quick. The sample rate variable is named underscore samp rate, and the value is 1e6, so 1 million, 1 megasample per second. Yeah, so just one moment. And the frequency is 433.92 E6 plus 62.5 E3.
And the reason we have this, that offset there, is that we had the documentation indicate 433.92 megahertz, but then we observed that the actual signal was 62.5 kilohertz above that 433.92. So we're just writing it that way to make it clear that it's, what we had documented plus what we actually observed.
Lies.
Sorry,
And then,
just go back to the variable frequency function.
yeah, sure.
I don't have the Osmo console, so I need to install something to be able to see it. I'm not running the
Yeah, so there's an Osmocom driver. It's gr-osmocom or Osmo SDR or something like that. It's actually a really neat block. Essentially, Osmocom is an abstraction layer for a number of other SDR drivers. So, like the RTL SDR driver, the Blade RF driver, the Hack RF driver, the way they interface to GNU Radio is through this Osmocom abstraction layer. So basically, you can use this block in your flow graph, and then no matter which SDR driver you have plugged in, it'll just work out nicely kind of behind the scenes.
And I believe the package, if you're on a Debian-based system, I believe it's a gr-osmo SDR, an app, so it should be apt-get installed gr-osmo SDR.
Sorry, one last quick question.
Sure.
In the Osmocom source, how are we changing the sample rate and the frequency?
Sure, yeah. So basically, when you open up the Osmocom source, you can just drop in the variable name, samp rate right next to sample rate, and then freq right next to channel 0 frequency. And it'll pass all those parameters in nicely.
Oh, okay, all right. Cheers, thank you.
Yep.
The WX GUI, how do you set you're setting?
Yeah, I went a little quickly through that. So GNU Radio supports basically two different graphics engines for doing a lot of the visual stuff. There's Qt and then there's WX. Qt is actually more modern and better supported, but we don't have Qt on this machine. So we're going to use the WX engine. If you open up the top block, which is this block up here on the left, this is kind of like the global settings pane for this graph that we're working with. Double click that and you go to generate options, and then on that drop down you have the option to select WX.
And in the underlying Python code that's generated when you run the flow graph, top block is just the class that everything else lives inside.
And then you'll be able to drop in whatever visual tools. You can actually drop in a waterfall. WX supports one. You can drop in the waterfall sync, and that'll give you a picture that's similar to Baudline that we were looking at. So if you don't want to go through the pain of installing Baudline and want to get a bit of a visual representation, we can plug this in too. One thing I recommend is if you do that, you pump the FFT rate up, because otherwise you just won't be able to see as much information. So it defaults to 15. I just replaced it with 60, and we'll see how that looks.
Sorry to be a pain. How do we change the sample rate to 1?
To here. Yeah. So type in 1e6. This is actually kind of confusing. GNU Radio will render it with K, M, or G to represent 1,000, million, or billion. However, if you put M in here, it doesn't process it. You have to basically list the variable names as scientific notation. However, it will display them using alphanumeric letters. So use E for 10 to the power, and then what follows E is the power. So, yep. So that's. What's that? Yes, the only thing to change the file sync is just the name of the file and the path, the absolute path. to where you want to write the data to disk. So here we just have a path to the directory that we're working out of, and then our file name, and then .iq to represent the data type, the complex data type. It's a convention you'll see. Sometimes you'll see IQ, sometimes 32IQ to say that it's a 32-bit complex float type. There's actually no strong convention for naming raw spectrum captures. There's a working group that some of the GNU Radio project leads are developing to actually define a metadata convention for describing signals, but they're academics, so it's taking years, and we'll see if it ever sees the light of day. So let's do this one more time. I'll tell you when. So I'm going to start this capture up, and Marc's going to trigger the. Actually, wait for it just a minute. There we go. Go ahead. So here we can see on the waterfall plot, we get a similar picture. And then let's stop that. Uh-oh. Crashing?
Yeah, I think it's at the close of the program.
Okay, cool. All right, cool. So has everybody been able to set up this flow graph ready to go? So I'm going to ask you to start capturing kind of simultaneously. Then Marc is going to play the real signal off of this device, and then you'll capture it, and then we'll try to open it up in Baudline and take a look. Everybody ready? Okay, no problem. So while you guys are wrapping up, let's just go back to our methodology and take a look at where we are based on our observations. So our open source intelligence research was unfortunately fruitless. There's no FCC ID. We plugged the product name into Google. We couldn't find anything. So unfortunately, we don't have any real hints with our open source intelligence research to go off of.
And this morning, I opened up one of these pagers to see if there were any markings on the chips, the RFICs on the circuit board. There weren't any, so it's really an unknown piece of hardware for us. So the open source intelligence process didn't yield anything fruitful outside of the tiny bit of information from the user manual.
Yeah. So to identify the channel, at this point we've characterized the channel. To do so, we basically looked at common ISM bands, and we saw 433 was where it lived. And again, ISM refers to industrial, scientific, and medical. And those are the permissively licensed bands that devices like this are allowed to kind of transmit without a special site-specific license with. And the common ones you'll see are like 315, 345, 433, 868, and then 915 megahertz. So those are like 5 sub-gigahertz bands to look at. And then the other common one that you'll see is 2.4 gigahertz. And that's where like Wi-Fi and Bluetooth live and things like that. So you really just have like 6 places to look if you don't, like if you're not able to find the channel in the documentation, you really just have 6 places to look to try to find the channel that or the amount of spectrum that it lives in. Then the remain for characterizing the channel is to identify the exact center frequency that we're at, and then identify the width of the channel. And since it's a constant frequency, modulation, there's no frequency modulation happening. We don't have to worry about that. So at this point, we've characterized the channel. We've identified the modulation because visually we were able to look at the spectrum and see that what was being modulated was the amplitude. That's the power of the signal rather than the frequency. Is everybody good up to here? Any questions about the process that we've covered until now? Okay. So the next step, we're going to kind of do this capture all together, and then we'll be able to keep moving forward through the process. And after this, I'd like to get everybody running in Spectrum so that we can use cursors to start to identify the symbol rate. So if everybody's ready, if your flow graph has any red on it, that means that you have an error to correct. But if not, then we're ready to go. So if you click on this play button, that'll start capturing it or start the capture, and then once that happens, I'm going to have Marc play the signal for us to grab. So if everybody's ready, on the count of 3, 1, 2, 3, hit play, and now I'll have Marc send the signal. Cool. There we go. So now you can just close your flow graph to stop the capture. And then that file should be filled up with data. And it's just raw data. I see somebody shaking their head.
So still errors on it, but it did start running WX2 at all.
It didn't? So if you think it's a problem with the GUI, you can just disable those blocks and just pipe it out to disk. You don't. Marc, would you mind taking a look? Cool. All right. Can you raise your hand if you were successful in running that? Got one. So some maybes. What's that? So you have a file, but it wasn't filled up with any. Oh, really? Okay, that's odd. I can generate the signal if you want to try it again. Okay. Okay, if anybody wants to try to grab this again, give this another go. Okay, I'm going to start playing the signal. Any luck? No. Still just all zeros in the file. Interesting. Oh, you got a few little bits of. Well, that might be okay. So we'll keep going, and when we open it up, there may be more there than you think. Because we have limited insight with the FFT that we're using. So that's just to see that we're looking in the right part of the spectrum. So, all right, so with the capture in hand, we're now going to go and try to look at it using these tools that Marc just showed off. So if you have InSpectrum installed, why don't you go ahead and open that up. As he said, I believe it's apt-get install InSpectrum if you're on a Debian-based system. It's in the main repo. And then you can run it just by running InSpectrum, and then that'll pop this up. Any questions or issues there? Let me close this out, and then I'll walk through it. So. All right, so with InSpectrum open, we're going to open that capture that we just generated. So just navigate to wherever you had the navigate to wherever you placed your file. Open it up, and then just within the sample rate block here, just type in whatever the rate was. So since we captured at 1e6, 1 megasample per second, that's the value we had in our variable. Just go ahead and put that in. And now, again, since InSpectrum visualizes the FFT with time on the x-axis, we can just grab this cursor on the bottom and just scroll across until we see our data. So anybody who just captured over the air, are you able to? Is anybody with me up to this point? Okay, we got one. We're trying to fit a lot into 2 hours, so appreciate your working with us here. Okay.
So if you stop that, then it should have that saved to disk.
Does anybody want a few more minutes to catch up, or is there anything I can walk through again?
I'm just looking at find the blocks. You did something, I just missed it in order to get to the right place where.
Sure. Yeah. So there, I mean, there are a few parameters to configure here. The power settings are manual, so you might have to kind of reconfigure this if your power min is set too high or too low. Is this like what you're looking at?
That's exactly it, just plain blue. Well, now I've got a sort of snowfield, just like you've got.
Okay. Well, that should be okay. So just grab your cursor on the bottom here. You see it's got the scroll bar on the bottom?
I just seem to have a different version of horizontal.
So Marc will take a look at that. But so if you grab the scroll bar and just slowly roll across, eventually you'll find your data once you scroll far enough ahead. And it should be visually clear once you find it. So now once you found it, you can use this zoom cursor to zoom in and increase the basically zoom in and increase the time temporal resolution here. So we can keep going, and ultimately we can get a nice picture of what's actually happening in the spectrum here.
Matt, do you know if any versions of the spectrum render vertically? Is doing exactly that? I haven't seen that before.
I don't actually. That's different. Let me try using that derived plot again. That didn't work earlier, because derived plots are awesome. It's looking awesome. Okay, cool. So I'm going to briefly walk you through adding a derived plot, and this is what I tried and failed at doing earlier with the first capture we had. Derived plots are really cool because basically in Spectrum has built-in demodulation functions that can be used to get basically better resolution when you're trying to figure out timing. You can just do it on the raw frequency plot that we have here, but sometimes using the demodulator can get even better results. So since we know we have an amplitude-based modulation, based on what we observed earlier, we can right-click here and say add derived plot, and then we can pick an amplitude plot. Again, amplitude because that's what's being modulated here. So click on that, and then what you can do is basically just align this this red bar, red line to be right in the middle of your signal, and then you can use these outer bars to basically control how much of the signal it's taking the power, or how much of the signal it's demodulating here. And what you'll see on the bottom here is that we've got kind of this low bit and then these peaks. And this is essentially the power response to the signal as we're moving along in time. So if we zoom out, we can see that this is starting to look like, what does this look like? It looks kind of like digital data, right? You have your ones and zeros, and ultimately these are the values of the symbol. If we view this, the center line is a threshold. Anything that's below would be a 0. Anything that's above would be a 1. So now the next step, if we go back to our methodology, we have a capture of the channel that we're looking for. We have a good sense of what the modulation is. The next step is to determine the symbol rate, and that's to determine exactly how fast that symbol state is changing. So we're going to do that using the cursors feature in Spectrum, which is really awesome and just a nice, easy, math-free way of doing this. So if we go back into Spectrum, we can click this box on the left here called Enable Cursors, and that'll drop these two vertical bars on the pane. We can drag the left one all the way over to the rising edge of the first symbol we see. Just try to line it up as well as you can. And then
Spectrum have some sort of enable advanced features about it, because we're seeing missing an awful lot of things. Not only is it rendering, it's
I wonder if,
lots of that you've got there, the time selection box.
I came across like yesterday, it might be that the package is slightly out of date compared to the latest source build.
it may be the case.
So did you compile this yourself?
I did, yeah.
So this version, I believe, is just from apt in Ubuntu 16.04, but it's possible that some other versions are out of date.
Okay.
Matt, if you want to alt tab over to Chrome there, I have the Inspectrum GitHub page open in the middle tab.
Oh, whoops, my bad.
Control-Shift-T.
Control-Shift-T. There we go. So the user is MIEK, and then the project is called Inspectrum. And I believe it requires Liquid DSP, which you should be able to install through apt. Just make sure you have the -dev package for the headers, so you'll be linking against it. And then you can just install this from source if you'd like to get the latest version here. So just, again, install Liquid DSP with the development headers, and then you can build this locally from source. And Inspectrum is kind of it's a newer piece of software. I believe it's only been out for about 2 years, but it's gaining a lot of enthusiasm because there's a lot of open source development behind it, and it's permissively licensed. So it's a great tool. It's got a lot of momentum, and a lot of people are starting to pick it up. I've become a big fan of it. So back to cursors. Basically, click on the cursors button. Drag the leftmost vertical bar over to the rising edge of our signal here, and then you drag the rightmost cursor over to the falling edge there. And usually, what you want to time is you want to try to time the shortest transition that you see. So you see here we have some signals that are, or some symbols where the high period is shorter than others. You want to try to time the shortest transition possible, because that's likely going to define your symbol rate. So once you have that lined up, you can just slowly start increasing the count here, and as you do it, just keep aligning the cursors here. And I'm going to zoom in a little bit more, try to line this up a little bit better. Then by doing this, it conveniently just tells us what the symbol rate is. So we haven't done any math, we haven't done any DSP, software's doing all the heavy lifting, we're just drawing pretty pictures on the spectrum, and it's doing all the hard work for us. So by doing this, we can make step 3 of that process nice and painless. Does anybody have any questions up till now? Don't be shy. Yeah, of course. Just the Inspectrum bit. Okay, sure. So let me start over. Plot, no cursors, and I'll zoom all the way up. So, the software, once you get the hang of it, it's pretty simple to drive. Just open your file, the file that you captured, plug in your sample rate. The sample rate you have to get right, otherwise the timing information won't the timing information that it tells you won't be correct. You'll still be able to visualize the spectrum, but basically the file that you captured there's no metadata describing its own timing. So you have to tell the software what sample rate it was captured at.
6. So,
6.
1 million for 1 mega samples.
Yeah, and that value comes from this sample rate variable block that we filled in the flow graph that we used to capture. So if you'd captured at a different rate, if you'd captured at like 500 kilosamples per second or 2 megasamples per second, you would just want to make sure that you're plugging in the right value for your capture into the sample rate block. And you can see that if you change the sample rate, it basically is just going to change the time. You can see as I change the sample rate, the time scaling up at the top of the plot there. Wait for it. There we go. As I change the sample rate, the time scaling is what changes. So you'll still be able to see it, it's just the timing information won't be correct. So once you have that plugged in, just come down to the bottom and there's this horizontal scroll bar, like you might see on any like web page or any UI. Just click on that, and just drag it across. Keep going until you get to your data. And you'll see your data just because it'll be the interesting bits of the picture here. You see what I'm getting at? Cool. You can zoom in. Just try to scroll to like the front of one of these. And then one of the neat features is you can add this derived amplitude plot. And again, amplitude because it's an amplitude-based modulation. If it was FSK, you'd do a frequency-based demod. Drop on that plot, set up the parameters nicely here, and you just kind of have to play with the outer bars until the demodulated signal on the bottom looks right, namely until you have those like really clean rising edge and falling edge on the data that you're looking for. So once you have that, you can zoom in a little bit more, drop on the cursors, just start with 1 initially, and then you can just line it up nicely with your first symbol that you're trying to look at. You're trying to time out. Then once you have that, you can basically just keep ticking it up, and then just make sure you keep adjusting it and aligning it as you get more precise. There's a little checkbox that says Enable Cursor right underneath Time Selection. And then you can, basically once you're comfortable with the amount of precision that you have, you can just record your sample rate, and with that in hand, you've determined identify the symbol rate, and with that in hand, you've completed step 3.
How many symbols do you want to line up until you have confidence in the...
So I would say that's it's kind of a personal call. If you're just taking one symbol, there's limited precision you'll be able to get just by virtue of how granular the UI can be. So you can go up as high as you want. Like we can, keep increasing this and make some finer adjustments. So this is 32, and there we go. So it looks like our symbol rate is approximately 3.69 kilohertz. So that's step 3 of our workflow here.
Now, does everybody have a capture with some of this data in it from the pager system? Was everybody able to? Okay. What was that? Okay.
Everybody who wants to, at least.
Right. Yeah.
Yeah.
last few seconds I've just been reading this message is lost of seeing just while you were speaking. You just saw the little spike, very like what you saw, the nice big carry on. You just saw the little crawl and what you wanted down.
Okay.
Just after that.
Okay.
Cool. So I don't have the picture in this slide deck, but I had it in the one yesterday. So essentially, there are a number of different ways that you can implement the software to actually do this decoding. But one of the ways that I like to do this prototyping is to implement steps 1 through 3 in GNU Radio, and then implement steps 4 and 5 either in like a bash script or in Python. And the reason why is because once you've determined parameters 1 through 3, it's pretty easy to implement that with a boilerplate GNU Radio flow graph, and that will do a lot of the hard math for you. And then in steps 4 and 5, which are the more protocol-specific and radio-specific features, you can iterate very quickly on kind of working through them. And I think the Python and Bash and tools like that are a little more comfortable for doing some of this more iterative work. So with that, I'm going to recommend that we, together we work through creating a flow graph to do this demodulation. So we're going to create a new flow graph. If we go back over to GRC, you can Control N. And the first thing we're going to do is we're going to set up our sample rate variable. And here we're going to make our sample rate the same value that we capture that file at. And the reason why we're going to do that is because rather than using our radio driver and having to constantly capture the signal from over the air, we're instead going to process the file that we captured so that we don't have to be always retransmitting, always working with the hardware. Basically, we can get a capture, verify that it's good, and then kind of cut the radio out of the loop and keep working with a known good source file. So the first thing we're going to do is we're going to drop on a file source. So if we Control F and search for file source, under file operators, just grab the plain old, normal one. We can leave the repeat option on for now, but we'll turn that off eventually. And then just put in right here the path to the file that you captured.
And the premise here is that it's just easier to deal with these files on disk than constantly dealing with the radio when you're going through this process.
Yeah, hardware's a pain, so we'll only deal with it when we have to. I say that as I was a double E in a past life. Hardware's a pain. Cool. So now we're going to basically do the, so essentially what the file source is going to do is it's going to read from the file those samples as fast as it can. And because with the solid state drive, it'll be able to do that really, really fast, we want to put in a throttle block to limit how fast it'll go. If you are using a hardware radio, you don't need it because the radio is clocked and will provide back pressure to basically limit the rate at which the samples flow through the flow graph. But if you're just using a file and there's no hardware radio, you need to put a throttle in. So you can Control F and search for throttle. It should auto-populate the sample rate from the samp rate variable. And then you can just go ahead and connect that from the output just by clicking from the source here to the sink here.
And this just mimics the rate at which we captured the data using the radio.
Exactly. It's not a requisite for doing the demodulation. It's just to keep GNU Radio from just like smashing your processor and just writing a bunch of nonsense to your hard drive. So the next step is we're going to essentially we're going to implement a demodulator that's essentially going to replicate what this amplitude plot did in Spectrum. And this is like by far the most opaque and intimidating part of doing this sort of wireless RE work. The thing I want to emphasize is that there are really just a couple types of modulations that you'll see. And you'll either be able to identify them visually or through the documentation. It will tell you what the modulation is. Once you have that, you can very easily go to Google and find a flow graph that supports the modulation that you're looking for, like just a boilerplate canned like FSK demodulation flow graph or a canned like 802.15.4 demodulation tool. And once you have that, you can basically rely on the work that other people have done, just replace the important variables with the values that we've extracted through steps 1 through 3 of our methodology. So the values that describe the channel, modulation parameters, and the symbol rate, and then you won't have to go through this process again. So basically what we're going to do is I'm going to walk you through making an on-off keying demodulator, but I'll also mention that the flow graph from yesterday that we're going to release is just as good. So you'd be able to replace the values there, and maybe that's what we should do. Should we?
Yeah, let's pull that up and just tweak the numbers. It's probably
easier. Okay.
On-off keying is one kind of corner case you can do in radio where there's no out-of-the-box flow graph or module or block for doing on-off keying demodulation. So we have to actually build one in this case.
Is everybody on the internet? If I were to put something on GitHub, would you be able to download it? Okay, give me 2 seconds. Actually, you probably have it on here, don't you?
Yeah, I've got hotspot up.
Okay, cool.
So it could be a port with a specific dongle, or with this. Typically, what I do when I'm doing any STR7 at the end is assign this device to VM, so VM always takes ownership. Okay.
What's it?
So one thing that's useful is to start doing a companion from a command line, and then you can get some console output that might provide some additional information about what's happening. So it's just a clean radio hyphen companion. USB stuff at the end is always exactly.
Hey, Mark. Can I get your creds? Show all these nice people the entropy of your password?
Yeah.
Actually, maybe this isn't the best way to do it. Just make sure it's not going to leak any data.
So yeah, I'm not sure why. I'm not sure why that's not working. So I have a hotspot up. Would you mind throwing it up through your laptop?
Yeah, no problem.
Yeah, just curious if that. Yeah, it's possible there's some sort of RTL modules. But anyway, yeah, unfortunately, I don't have any better insight. So yeah, it's the hotspot that should be up. So. Okay, so this is a repository where Matt is uploading this flow graph. It'll be up there in just a moment.
Good. Going to refresh that page. Cool.
Okay, so the flow graph is in this 44con folder in this So You Wanna Hack Radios repository on GitHub. And this is a flow graph from the siren that we demonstrated in the talk yesterday. It's another pulse width modulation on-off keying device, and so we can just tweak some of the parameters in this flow graph to match the timing that we're using with this pager system.
Cool. So you can either clone this repo and copy it that way. Otherwise, you can just navigate to the web page where it says raw. You can right-click and just download the raw XML basically. Just name it GRC so that GNU Radio Companion will recognize it. And then once you have it on your system, we'll keep moving with it.
It should be open in the GRC already.
I made a couple changes, so I'm gonna just pull down so that we have the same 4con pager siren RX to GRC. Cool. So you should have a picture that looks just like this once you have it open. Is everybody good up until now? Everybody who wants the flow graph has it? Cool. Right on. Okay, so basically what we're going to do is we're going to begin just by renaming or reconfiguring the variables to match the parameters that we're looking for, or to match the parameters that our new signal will abide by. And again, the reason why we're able to reuse this is because this flow graph implements the same type of demodulation that we need to perform for this sensor. Because this siren was an on-off keyed protocol, as the pagers are, we can essentially just reconfigure this flow graph, reuse it. We don't have to worry about any of the math that's going on, and that'll be nice. So the sample rate we can just plug in here. The frequency we actually don't care about because we're working off of a file, so we won't even have to worry about that at all. Same thing with the offset. So why don't we begin just by disabling all the radio-specific stuff that we're not going to need. So it's very easy to do in GNU Radio. You just click on a block, and then you press the D key, and you can basically comment out blocks. So we're going to begin by commenting out the radio, and then commenting in the file source here, because that's kind of like a secondary input. The one thing we'll have to do is we're going to have to connect the throttle through to the complex to mag squared block. So click on the output of the throttle block and the input of the complex to mag squared, and that'll work out nicely. And then the other thing to do is just to update the file path from the file source block, because right now it points to a location on my hard drive. I doubt that's where you stored your capture. If you did, please talk to me. So just update that path to reflect the capture that we're looking for. In the file source block. So it's right up here in the middle. Just plug in the path to the capture that you grabbed.
And if anybody has any questions about changes to this flow graph, let me know. I'll come give you a hand. Yes.
Oh, to uncomment, you click and you press E.
Yeah. So it's D for disable, then E for enable.
I think those are available through Edit as well. Is that right? Yeah, they're called enable and disable. So basically we've disabled the frequency offset, UHD source, and rotator, and then we've connected the throttle through to complex to mag. So basically the complex to mag and then the log 10 is going to take our signal and compute the power of it. So what comes out of log 10 is actually going to be a floating point value. We know it's a float because orange is the type in GNU Radio Companion that refers to float. So basically, this is converting from our complex radio signal to a floating point value that represents the power of the signal. And then 10 log 10 takes that and normalizes it on the dB scale, which is a little more conventional than whatever this produces. So then the next thing we have to do is we have to update our symbol rate variable, our symbol rate value, so that the clock recovery block will do the right type of basically resampling. So essentially what the clock recovery block in this case is going to do, it's going to do a little bit more, it actually does quite a bit more than this, but the reason why we're using it is because it's going to take the sample rate that's coming from our file and basically do some math and work it out so that the rate that comes out of this is our symbol rate. So if we scroll down, we've got the symbol rate variable. Just double click here and replace it with the symbol rate that we got out of Inspectrum, which is 3.69 kilohertz. So 3.69 E3, E3 for K. And then that's populated there. The sample per symbol value will get updated automatically. And then that is what is in the clock recovery block. So that all just works out just by renaming these variables. The threshold we might have to play with in a minute. We'll give it a test and see. The last thing I'm going to do is I'm going to change the path of this file sync here. So what this flow graph is going to output is essentially just a stream of ASCII ones and zeros. Not ASCII. What are they? They're just 8-bit values that are either the binary value 0 or binary value 1.
And this threshold block, so this is telling us to output a 1 or 0 based on whether it's above or below this certain power level. And again, we're modulating this data. It's amplitude modulation. So if it's above a certain power level, it indicates one value. If it's below that power level with the radius off, it indicates another value. And so that's just telling us a value at which we say it's a 1 or a 0 at that decibel level.
So the last thing to do before we run this and see how it looks is just to rename this file path here. And you can just put it anywhere on your system that works for you. Scratch, that's right. Pager, and we're going to call this pager
Dmod.
Pager.dmod. Cool. And one other thing I'm going to change is I'm going to change the append file to overwrite. I had it on append because previously I was running to a FIFO, like a named pipe. But since I'm running to a file now, I don't want the file to just keep growing every time I run this. So changing from append to overwrite will make it so that we basically blow the file away every time we start writing to it. So is everybody caught up until now? Any questions on the changes that we made to the flow graph? All right, so now we can just save these changes here, Control S, and then we can run it. And the first thing I'm going to do is I had this WX scope sync here. I plugged this in after the threshold block just because I want to see exactly where the power is coming in from the signal that we captured, so that we can see whether or not that's slicing, that 1 and 0 slicing is going to work out properly. So I'm going to hit play. There are some neat features here, like cursors and things like that. Not seeing anything. So I'm going to go a little further up the chain and validate that we're in fact getting data out of this, or out of our file the way that we expect. So I'm going to copy the scope sync. I'm going to change the input type to complex, just in the type. And then I'm going to change the sample rate that's expected here to our samp rate variable.
You want to check the terminal output from GRC in case there was some file system problem or something.
That's a good point. Where
It's that middle one there.
this here?
Okay, yes. Okay, so no problems there.
Looks fine. It's a good idea. I'm going to disable this. Oh, scope, sorry. I used the wrong block. I didn't intend to use a scope block. I wanted to use an FFT block. So WX FFT. This is the same one that we used earlier to validate our capture. Okay, cool. So we can see that if we turn on the peak hold, that we are in fact, the file is producing samples as we expect. Wait for it. There's our signal right there. So that's all looking good. So now we can basically take this scope sync and keep moving further up the chain to validate kind of each step as we go. I'm changing the sample rate here to the sample rate variable because we're before the clock recovery block. So data's flowing at 1 megasample per second up until this block, and then it's flowing at 3.69 kilosamples per second after that block. This is odd. I'm going to clean this up a little bit so that I can see a little more cleanly. So this button here will just hide commented out blocks, which is kind of nice. So go ahead and do that.
This is basically the GNU Radio equivalent of adding some debug printf statements to your C code to figure out why you're not getting your correct output.
Okay, so this is working. I just have to get these values set right. Take this up a little bit more, and okay. So does this look familiar to anybody? This plot that we have here. It looks kind of like the demodulated signal that we saw in Spectrum, right? It's not rendered as nicely because we're downsampled as low as we can be, but here we have the same high, low, 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 high, low, low, low period that we see right at the beginning here. So with that validated, oh wait, there's one more thing I wanted us to look at there. So if we go back to what we just had, if we wait for it, stop it here. We can look at the axes here to basically look at our normalized power readings that we're going to be using to determine the threshold on what's going to be a 1 and what's going to be a 0 valued symbol. So we can basically just look at this, pick a value that makes sense. We want to pick something kind of right in the middle, maybe a little bit towards the top, because we want to be high enough above the noise floor. I'll say we'll set our threshold to around -50, just because I think that's a reasonable call. And then we can come down here and just update this value accordingly. So -50, -50. Oh, wait a minute. Now I'm going to put our scope plot down below so we can validate. Run this again. And this is looking good. So basically what we expect now is this flow graph is going to produce a stream of, basically binary valued zeros and ones that'll go out to this file sync here. And then that's going to get written out to disk. And then we're basically just going to have a binary file that's filled with the symbol values that we've just demodulated. And with that file, we can then take it and parse it using any tool we want, whether it's Bash command line tools or Python. We can start to visualize that data and parse through and try to frame the packet. So that brings us to what's really step 4 of our workflow here, which is to identify the preamble and start to synchronize against the packet. So let's just jump back over to Spectrum and visualize what's going on here. What do we see at the beginning of the packet? Anybody care to hazard a guess as to what denotes the start of a packet? Yeah, so we're looking for a preamble or some sort of repeated signal. And here it looks like the preamble or what denotes the start of a packet is a 1 valued symbol followed by 3 low valued symbols, or 0 valued symbols, followed by another 1 valued symbol, and then 3 more 0 valued symbols. So we can essentially implement some software either through grepping through the file or in Python, looking for that sequence of bits, that sequence of symbol values to denote the start of the packet. And then once we found that, we can dump out the next, say, n number of symbols and use that to frame our packet. Is everybody good with that conceptually?
Might be good to show like the radio hacker.
Yeah, that's a great idea.
There's a tool that I've only played with a little bit in the last few days. It's called Universal Radio Hacker, and it was demonstrated at Black Hat Arsenal this year, and it automates part of this process. So I'll just pull it up really quick.
Is that on apt-get?
I'm not sure if it's an apt. I'm not sure about that. So this tool, you can give it an IQ file, and then it will attempt to infer some of the parameters, some of the properties of the file, but generally you need to give it the timing. But we're going to go ahead and open up this test.rx file here, and we're going to here, so we're going to set the modulation to amplitude shift keying. Say show as hex, and in this case it's actually been able to automatically infer all of the parameters of the file. And so in this case we just give it a IQ file, and then it's actually pulled out these payloads from the file. Usually it doesn't work this magically and this correctly. So in this case we have the hex character 8, that's going to be our 1000, which is going to be the 1000. And it actually was able to pull out all these packets in the file. So Universal Radio Hacker is a tool that, at least in some cases, can shortcut part of this process. In my past experience with it in the last few days, I've had to manually configure the timing information, which is this bit length value. But it's a tool that's gaining some traction as a way to kind of more easily automate part of these processes. And so in this case, we've seen all these packets in here, and this is also telling us this value of pause a number of samples. This is the spacing between each packet. And so it's kind of a cool tool, when it works well like this, to really quickly pull the payloads out of those IQ files.
Would it be a ton of pain to turn off the auto detection and plug in the values that we pulled out of our process?
Yeah, exactly. And so the two parameters here which we need to set are the modulation. So in this case, amplitude shift keying. This is just our amplitude modulation. And so when I open the file, it was set to frequency shift keying, which was incorrect, but set it to amplitude shift keying. And then this bit length value, this is going to be our samples per symbol. So this is our sample rate divided by our symbol rate. And we can just compute that easily here. So we have our sample rate, in this case, was 1 megasample. So that's 1 million. And then our symbol rate was 3.69 kilohertz. So that's 3690. And that gives us this value of 271. In that case, I was pretty close to what Universal Radio Hacker inferred. And then it recalculates when you adjust those. And let me just do one more quick example here with this presentation clicker we had in the talk yesterday. This is a frequency shift keying signal. So in this case, this was a not quite the same auto detection. So with this presentation clicker, we had a 10 megahertz sample rate. We had a 1 megahertz symbol rate, which we determined using in Spectrum. And so that gives us a samples per symbol of 10. So we put that in there, bit length of 10. And then down here, it's showing this binary output. We can say show signal as hex. And then this gives us these payloads that were sent over the air. And so it's a kind of a neat tool. I need to play around with it more myself, but it looks like at least a potential way to shortcut some of this process.
So basically, had we not used URH, what we would have done is we would have basically just written some software to look for that pattern that denotes the start of the packet, that 10001000. And we would have basically used that to denote when we found the start of a packet. Once we do that, we would dump out the next number of samples, which you can just determine either visually or arbitrarily. Just pick a large number of samples, kind of print them out, and then you'll be able to start looking for patterns that denote activity within or denote certain behavior within the packet. So maybe we can do briefly, because we're pushing right up on the end of our time here. Maybe we can set up 2 different pagers, capture them, and then we can look at them in URH and visualize how we can start to see differences in the.
Capture that also pagers. That's a good point. So this way we'll do a quick capture with 2 different pagers, and then run that through URH, and then we'll see the 2 different payloads there. This is generating data with known different inputs is a pretty good way to start to figure out what the packet format is, because then we can make some assumptions about what parts of the packet change when different input happens.
Okay. So we'll hope that came through. And let me see if I can figure this thing out. URH.
Yeah. Oh yeah, definitely, yeah. Yeah, I'll just sit here and set pages off for a few minutes.
Okay, so what I'm going to do is I'm just going to create a text file. Then we can just copy out some of the more commonly seen packets here, and we can start looking for the format. Do you have a text editor?
This is black, this is yellow.
Sweet.
And if you have a new window file, new window. Yeah, there you go.
Okay. So go back over to URH. I'm just going to copy one of these if I can. So that's the first.
And then I think there is.
Was that?
Yeah. That looks pretty good.
Does it? Okay. And then go a little bit further down.
Oh yeah, that's better. Yeah. Other one was
Yeah.
just a tiny. Yeah.
CSOF 3, right?
Yeah.
Cool. Okay, so here we have, basically what I did is I just scrolled through URH and I found packets that look like they would be representative of data coming from each of the 3 pager systems that you set off, because you set off 3 different pagers in that capture that we generated. So now we can just take a look here and we can visually see the fields that are changing based on the address that he sets off. So we've got our preamble that we're expecting to look for. Looks like we have some kind of header that follows it. You know, we don't know for sure that this is what it is, but I suspect that it might be an address associated with the base station. If we had 2 different systems, then we could test and see if there was a difference in this field. But the thing that we know for sure is that these 3, at least these 3 spaces right here represent the address of the pager that we're trying to call, that we're trying to transmit to. And we can just visually see that within the data. One other question, you know, why 8s and why E's? Any intuition for why these are the values that we're seeing?
That's 8 is going to be the one with 3 zeros out of it.
Yep, exactly. So as we saw with the siren yesterday, this data is encoded. So in this case, it's not a one-to-one mapping between symbols and bits. Instead, we have what I believe is a 4-to-1 mapping for symbols and bits. So we basically need to decode the symbols from their encoded state to get back to their real digital values. So it looks like it's actually using very similar encoding or the same encoding to what the siren is using, where it's likely that this 1000 pattern equals a logical 1 or a logical 0 or logical 1, one logical state, and then again that's 0x8, right? And then the 0xe that we're seeing is likely 1110. Or it is 1110, which is likely the other logical 1. So we can, you know, even just like take this and just find and replace those values, because they're already nicely decoded in hex, and get back our decoded binary payloads here. Does that make sense? Everybody follow me through that? I kind of talked through it quickly. And this encoding is the sort of thing that you might see from a data sheet. You might just have to work it out over the air, especially when you get to some more complicated encoding schemes. Like some protocols will nest them, and you have things like error correction as well, but that gets more complicated. So, any questions so far?
I think we're about the end of the time.
Acknowledge we had to move very quickly at the end here.
All right. Well, thanks, guys.
Does anybody think that this was at all helpful or useful? Okay. Well, so we can just go ahead and wrap up. Just to wrap up, we basically proposed this methodology for how we can provide structure to this reverse engineering process. And the key element is to start it off with some strong open source intelligence research, and then methodically work through the signal to identify the key characteristics that you'll need to plug into a flow graph. So the first step is to characterize the channel, and as we saw by looking at this system, it was a single channel in the 433 megahertz band. The second step is to identify the modulation, which, and again, this isn't filled in because we did this all together just now. Identifying the modulation was an on-off keyed modulation, similar to the siren that we saw yesterday. Symbol rate we were able to recover using in Spectrum, which was 3.69 kilohertz. Synchronizing, we were able to theorize, or at least talk through using by looking at it and identifying the preamble, the 1000 1000 repeated pattern. And had we implemented this in Python rather than using URH, you'd just be able to process that bit stream and look for that pattern, and then just grab the next n number of symbols, work with that. And then finally, step 5 is to extract the symbols and do that decoding, which again we talked through, that mapping between 8 hex and E hex back to 0 and 1, and then visually look at the packet while you kind of fiddle with parameters to see which fields control which parameters in the packet, which we saw by the changing addresses within the 3 packets that we pulled out. So essentially what we've been able to do is we've been able to use this methodology and apply the same process, the same steps to reverse engineer at this point 4 different wireless physical layers. We saw the 3 yesterday, and then we saw this one today. So, if you guys have any questions, we're around for the rest of the day today. We're happy to hang out and go through any more of these steps in detail if you want more one-on-one or have any questions. There's our contact information. Feel free to email us or hit us up on Twitter if you have any questions about this, or if you go home and you're working on a wireless protocol and you want some help with it. We're always happy to help out with this. The other thing I'll plug is the open source SGR community is pretty spectacular. So if you go to hashtag GNU Radio on Freenode, there are always a lot of people hanging out there and usually super willing to help out. And there's a new SDR project seemingly every day. There's a lot of momentum behind the space right now. So if you have any questions, consider us resources. We're happy to help. And I just want to thank you guys for coming and participating and playing along. And we had fun. Hope this was useful. So thanks.